So the lecture today is called Bayesian Statistics and Deep Learning, and it's mostly about statistics though. So I can show you some deep learning, but honestly, to set it up and do some practice, it would take a whole bunch of time, and I expect you are all tired of installing all the packages. So I mainly plan to speak about Bayesian statistics, but if most of you want more deep learning and less statistics, you can tell about that now, and I will improvise something about that. So is there anyone here who really wants deep learning? Raise your hands. 1, 2, 3. Well, I can tell it to you over the lunch. Yeah, who wants statistics? Oh, a lot of people. Nice, nice. So, and then again, part of my explanations will be there with actual math and, markers. So I want to ask you all to really ask a lot of questions. So let's make it interactive. Anytime you don't understand anything, because everyone has different backgrounds, and I can easily say something which you don't understand, so please stop me, yell, throw at me something, but yeah, make sure that you understand what I'm saying. So the first part, there is Bayesian statistics, but there is also classical statistics, frequency statistics, and who knows the difference? Do you want to tell?
Some standard statistics you test statistical hypotheses, and Bayesian statistics you take into account prior knowledge and based on evidence available you update that knowledge. In frequency statistics you don't take into account what is known already.
That's one way to go about that, yeah. I would say more formally, you're correct, but more formal difference is that frequency statistics assume that we have an observation, and let's imagine that we repeat this 1,000 times. For example, I come here, I give a lecture, and if I would do it 1,000 times independently, what's the probability of the lecture to be good? So that's kind of unrealistic, I will not come here 1,000 times, and they would not be independent. And Bayesian statistics has a very different approach to probability, and that would also kind of be connected to the lecture on cancer evolution, which Gustav will give you, that in Bayesian statistics, probability is a measure of uncertainty. So we assume that actually the world is kind of deterministic, so we can infer all the processes, but we don't know much, so I don't know if it will be good or not. I hope so, but if I would know all the variables, I could predict all the future, and then I could build a deterministic model. But lack of knowledge forces me to basically to account for uncertainty, and that is a probability. So probability is a measure of uncertainty, and that's pretty crucial. So as was said, in Bayesian statistics, we also try to take into account different priors, and these priors, basically, it's what we already know about the world, and that's what reduces our uncertainty. So, current knowledge can help us make probabilities closer to 1 or 0 instead of complete uncertainty. So, still, let's get back to the frequencies approach and see how it usually works. It's to understand when it is good and what is not. So, for example, real study, most of studies with molecular biology, you have some, for example, stains, then you count some cells, or expression of some gene, so which cells express it and which don't. Then you estimate difference between that number of between the numbers of cells, and then you may say the difference is significant or not. So who of you did or used results of statistical tests at least once? So yeah, all of you. So you know how that works. And then when you get your results, you make some conclusion, like observed decrease in probability levels and synaptic contacts might indicate impaired maturation of probability plus interneurons. So basically, you see this plot and you write this conclusion. But then it's totally unclear, like, what exactly is this p-value? What does that mean? And how, having this simple number, we made this long conclusion? And sometimes, usually, they are even longer. So, first question, what is p-value? Anyone ready to answer that?
It's the probability of taking some observation if no hypothesis is true.
Correct.
Sorry, just can you go back to the previous slide?
Yeah?
Because here this is quite common, let's say, obstacle in the statistics-based studies. I see in almost each biological study, because we use p-value to quantify the significance of our studies or our results, but we have to remember that p-value is not primary result of our study. It's extremely unmeaningful from the point of view of biology. Therefore, for example, in my studies, I strongly recommend my students and co-workers to provide an effective metric of effect size along with p-value. And instead of, for example...
We will get to that.
Okay, sorry. So, I mean that I would like to see p-value with effect size method, appropriate effect size.
Okay.
Simply p-value is not enough to interpret if it's biological interesting field or it's not. Yeah? That's the point.
So, yeah. Well, it's true that p-value is like probability of observing the difference given the null hypothesis. But who of you has the intuition about that? What that actually means? Like, almost none. And that makes sense because it's totally counterintuitive thing. So let's look at it. Like, we have some mice with drugs, without drugs, and we compare their weights, and we do one experiment and see that the weight difference is like minus 10 grams. So the null hypothesis in this case would claim that there is no difference, that all mice came from the same group, and basically we can split them however we want and estimate this kind of difference for random splits. And then we can repeat this like a lot of times, just do random splits, and estimate difference of means. So like in case of this random stuff. And assuming that all the splits are random, the question is like how far we would expect our original difference to get onto this plot. So like before we had this minus 10 grams, and now we see that it's mostly like 3 or 5, but not much. So like minus 10 is here, so we expect like the difference to be this far from the mean in like this small percentage of cases. So that is p-value, and basically that is our chance to make a false decision to say that there is difference while there is none if the null hypothesis is true, which means that if there are really no difference. So any questions about that definition? Because it's like kind of crucial to understand how p-values work. Anyone who does not understand it and want me to repeat or rephrase?
Yeah, maybe you can repeat one more time.
Sure, thank you for telling that. So the idea is that let's assume that there is no difference between our groups, that this observation of minus 10 is just by chance, completely random, because we could split them in different ways. So the probability to find a large difference just by chance, while there is no difference at all, that is our p-value. So, well, then the question is, what's wrong with it? And a two experiment is like, you may say, like, you are walking in the real world, and a stranger comes to you and gives you an apple. Just, some random stranger in black robe gives you an apple. And you want to understand if it's poisoned or not. So hypothesis 1 is that it is a wizard, and the apple is like magical and poisoned, and you will die. The hypothesis number 2 is just, a random guy who wants to share an apple with you. Or like hypothesis number 0. Let's assume that in our world, like, if a wizard gives you an apple, it's like 90% chance, he will turn you into the frog, and 5% chance it's just normal apple, and the wizard, miss his magic. And if it's a random guy, it's 100% true. So, if this is like our null hypothesis, and these are our probabilities, basically, that's kind of how statistical tests work. So, like we say that if we want to test for difference, we have like hypothesis 0 where there might be difference with small chance, but usually there is no difference, or hypothesis 1 where there is a lot of difference. So, like in this example, what do you think are your chances to get, to be turned into a frog?
Zero.
Correct, because your prior is you're 100% certain that there are no wizards in the real world. No one can be turned into a frog. So you can do statistical tests, but basically if you have a prior knowledge that it's all bullshit, you should not do that. And that's the thing about statistical tests, what we discussed from the beginning, that there is no prior knowledge. You may read like 100 papers about some experiment claiming that something cannot happen, and then you do one experiment which shows that it can, but still you would do some statistical tests, still you would show it, but how would you incorporate those 100 studies into your model? How would you say that it's not enough to have just one experiment maybe? And here is like a table to show how really it's so counterintuitive. So you have prior knowledge, it may be like 95% chance of real effect, 50-50, and 90% chance that there is no real effect, and 10% chance that your experiment is correct. And then you get p-values like 0.05, 0.01, and what you want to understand is the probability of having a mistake. So, because p-value is not a probability of having an error, it's a probability of seeing a difference assuming the null hypothesis is true, which is not what you usually care about. So, if you have a prior probabilities, from p-values you can estimate probability of you being mistaken. So, if it's 50-50, so if you are completely uncertain, then both these p-values, even if your p-value is 1%, then the probability of having a mistake is 11%. So it's not exactly what you care about controlling for, and only if your chances 90% versus 10, then p-values kind of represent your probability of having an error. So any questions about this slide? Yep. So you want to measure probability like that there is some real effect. And this is so you made a test which shows you that there is a real effect. And you got p-value like either 0.05 or 0.01, which are like popular thresholds. But imagine that you have prior knowledge about chances of having a real effect. So if your chances of no real effect is like 95%, so if you go against most of the literature, then even if your probability, like even if your p-value is 0.01, then 70% it's likely that there is still no real effect, and like experiment just give you some random stuff. So you need to have like p-value of something crazily small, or do a lot of experiments showing the same things, independent experiments, to be sure if your odds are really weird. Because like, for example, if you discover do drug discovery for cancer, then like the probability that a random molecule would cure cancer is super small. So you need to show a lot of experiments, and having just one tiny p-value is so much not enough that you should be very careful about that.
And then probably you should tell how would I estimate my knowledge, my prior knowledge, and the chances.
Well, it's not easy and really depends on cases. Like, basically, one trivial way to do that, it's like super rough, but imagine that there are like 10 independent publications like showing that there is no effect, and your single experiment showing that there is effect. So let's tell them that your chances are 10 versus 1. So you can kind of put your priors, at least like you may say that is it more likely or less likely than 50% that your study has an effect. So before making a study, what was your guess, like would it work or not? And often we can say from the beginning that we are doing some weird stuff and it's very controversial and the chances are pretty low. Any other questions? So that's the first problem with p-values, that they don't show you the probability of having an error, and it's untrivial how to incorporate priors into them. I mean, it is possible, as you may see, but it's not trivial. And complex priors are much harder. The second hypothesis is the stuff which people conclude from having a few p-values. So basically, all the p-value tells you is that there is a difference between two groups, a difference between these two groups, and no difference between these two groups. And there can be like tons of reasons why we observe this difference. Like, really, maybe different experiments, maybe batch effect, maybe chance, whatever. Well, chance is kind of controlled for, but not really. And people do really complicated conclusions about the underlying biology and what caused those changes, even though like there is no transparent process of how to translate those conclusions or connect each part of the conclusion to our p-values. So yeah, having a significant p-value does not translate directly. Here's like, though I'm guessing to save some. Yeah, no, that's the important part. So like study, online editors do better in the marriage, and that's the third problem with p-values. So study of 19,000 people, they claim that you see with these tiny p-values, people who met spouses on online apps are less likely to have high marital satisfaction. More likely, sorry. But if you look at the numbers, like divorce rate, difference is less than 1%, happiness is like, again, some tiny decimal difference. So that's exactly what was brought to us before, that p-values do not show you size of the effect, and often they hide it, so people deliberately do not represent it, because it's like, it's the effect which we do not care about. So, as a conclusion, there is a whole bunch of things which are wrong with p-values. To clarify, I don't mean that you should never use p-values. P-values are very helpful in many situations. They help you to understand if the difference you observe is real or not, or like more or less real or not. So it does not mean like the conclusions are real. It does not mean like it's hard to compare against the prior, but at least in a single experiment, when you see this difference, you may say that it's not random. Most likely it's not random. So using p-values is still good, but like in narrow set of cases. And now I will finally get to Bayesian statistics. So if you have any questions about p-values or how to use them, how not to use them now, like just ask it now or over the lunch. Yeah, please.
Regarding your hypothetical question about the wizard and the apple.
Yeah.
If you know that the idea was wizards don't exist, so 100% chance that you won't turn into a frog.
Yeah.
But if that is the case, how would you know that there is a 5% chance that the wizard gives you an apple?
You might be read it in a book. I don't know. Oh, no, I mean, yeah, it's a example made up like from my head, so. Yeah. No, I mean, feel free to ask these questions as well. There. Also, I might be mistaken somewhere, so yeah, if you ask such stuff, we may uncover it. Yeah?
But in general, the lower the p-value is, like, if you have extremely low values, we can trust it. So, like, when we get common, like 0.05 or 0.01, I mean, yes, there's definitely some less probable likely to happen, but the lower the p-value is, the more certain we kind of come, right? So the more robust the p-values are, the lower the value. Or that still doesn't...
That does. That is correct. So the smaller p-value is, the more certain we are that the difference we observe is real and not chance. But, for example, like, I will get to it a bit also later. Let's get to this idea with stainings and cell types. So imagine you took your staining and just, like, on the simplest level, you take one staining, quantified some cell types, and got a p-value. Can you, like, is it really hard to see what I'm writing here? No? Okay, cool. So then the p-value, I mean, even if it's small, maybe let's 0.0001, it would tell you that on this particular staining, you see the difference between cell types. The question is like how it translates to a hypothesis about all individuals, all brains, whatever. So you may assume that, like, first of all, it does not account for inter-individual variability. So p-value for one staining only says you about one individual. Then, of course, you may add more stainings. So let's repeat it like 1, 2, 3, 4, 5, and estimate another p-value. Maybe it's still small. So that would give you a hypothesis about multiple individuals, but then you would understand that maybe you are biased by, I don't know, age or sex, and they're not very representative, but you still can get a small p-value. So maybe you need to add even more. then it still could give you a small p-value, but maybe it would not translate to different brain regions. So again, like more samples from different brain regions, and then you can go like, I don't know, to thousands, whatever. It's really expensive. So hopefully you would get a small p-value there, but I can also imagine a whole bunch of problems with this approach. So the question is like, really small p-values give you trust that your current experiments shows you real stuff, but it does not tell you anything about representativeness, anything about your final conclusion. So it's not a model, it's like single observations about single set of data.
Okay. But the more we add samples, we go to inference, so we get to the ground truth. So adding more samples and getting low values would mean that that's probably kind of ground truth.
Yeah, I mean, like, it just that you need to add samples carefully, you need to choose your hypothesis carefully. So, like, there are a lot of things about experiment design, how you can do that, which you may know from other sources, but p-values do not help you to do experiment design. And I will show you later, or like now, that Bayesian statistics does help you, and it tells you exactly how to do that. Other questions? So, that's what I was talking about, is comparing like models versus hypotheses. So, p-values help you to test hypothesis, a single one about a single difference, and get an answer about that. But in biology, you usually like care more about models. So what can be a hypothesis? Linear regression has non-zero slope. So you may look at the data and say that indeed, maybe it does have a non-zero slope. So it's not flat. If you speak about models, then you say that dendrite length of neurons is proportional to age of individuals multiplied by some constant, which is kind of representing slope, and plus some noise, so which is, what does not make the line perfect. And then we say assumptions about noise. So classical one is that noise is normal with some zero mean and some standard deviation. So that's our model, and that's much easier to test against the data. So like it's much more connected to what we care about. So for example, here, if we would explicitly test for this model, we would also obviously need to test for noise, like if it's actually normal, and we would see that it is not. So like classical linear regression just is not a suitable model here, which we have as some hidden underlying assumption in our hypothesis, but it was never said explicitly, so we don't expect, we don't remember just to test for it, and also it's kind of hard to modify. So for example, if we would want to change our noise model, like maybe it's Poisson noise or like Cauchy noise, whatever, then we would have to, I don't know, either manually implement a test for linear regression, like find some appropriate package. So it's just, something which we are not forced to think about, though we should. Then again, in our model, we may have prior knowledge about the slope. Maybe we know from previous studies, maybe different people showed you that the slope we expect to have is this one, and like that it might be somehow like around 0.2. And that kind of knowledge we can also test. We can see how well this model would fit our data. And that's something which is really hard to test against, like just by hypothesis. then again, if we have two models, we can compare those, like prior knowledge, like having prior knowledge, not having prior knowledge, like testing two models. So like in hypothesis testing, we usually compare like hypothesis 0 and hypothesis 1, and hypothesis 0 is always something trivial. Here we can take arbitrary number of models and pick the one which is most appropriate. So we can have several like possibilities of how the data was generated. We can describe each of those, and we can put prior probabilities, like our confidences about them, and then we can pick the one which we think fits the most. Anything? Any questions about this part? Is it clear? Is it not? Yeah.
Just picking the one that fits the most, is it actually like correct? Because like seeing that something gives you a good metric or something, does it actually also mean that it's the correct one? Because you go by because you see a metric that's better, but does it actually represent truth? Or just it happened to fit on the...
You know, as they say, all models are wrong, but some are useful. And that's totally true. I mean, you can never say that a model is correct. But like the same with physics, like take Newton and physics, we live in it, but it's wrong. So like it does not represent reality. Like I think that I can touch the table, but you know, it's not solid. It's like mostly emptiness because there are like these atoms very far from each other. So like we live in models which are not correct, but it really helps us to simplify the truth and deal with it somehow. So yeah, most likely it will be wrong. Did I answer your question? Yeah, cool. Anything else? Okay. Then, when we speak about dealing with models, there are usually two phases. One is exploration. Basically, you just collect lots of data and look into it and build a model. In case of like biological experiments which we are teaching about here, is like single-cell RNA-seq, for example, is mostly this exploration stage. You just know, you collect your data, you test, I don't know, 20,000 genes, you pick 5 which you think are most relevant, and you cannot trust that. So you can hope that they are relevant, but just the data is so noisy, and you tested so many hypotheses, that it's really not trustworthy, but it gives you some idea of what's going on. So that's the exploration stage. And then there is a second stage, which is confirmation. So you made a hypothesis, you build a model, and then you say that maybe this gene is expected to affect this gene, and they together would, I don't know, make a mouse smarter. So then we can finally make experiments to test exactly that hypothesis. First, that the genes are affecting each other, then that together they are making a mouse smarter. So from this like set of hypotheses, a set of models, we can design new experiments and make sure that they show exactly our models and perform them, and that's a confirmation step. Most of all, when you publish a study, you are expected to perform both, though there are a lot of studies which just publish, you know, single-cell atlas of Alzheimer, and that's purely exploration stage. You cannot trust it completely, but it helps you to make further studies which might be purely confirmatory. And getting back to p-values, usually on the exploration stage, you just are looking for most interesting, like most powerful facts, and you don't necessarily test against significance, you just pick the ones which are most likely. And the confirmation stage, I mean, it's kind of not true that I wrote here don't use p-values. They might use p-values, but if you do like model testing, then there are a lot of ways to do that, like in Bayesian way, without p-values. So the point is that it's theoretically possible to live like in the world without p-values completely, and do a nice study and be pretty confident that it's correct. Yeah, p-values might help, but they're not necessary. Questions? Are you still on board with me? Cool. So then, confirmation. If we don't use p-values, how would we confirm that our model works? One thing which is very popular is Bayesian factor. So this is just reformulation of hypothesis testing in Bayesian terms. So you have probability of observing your data given null hypothesis, probability of observing your data given alternative hypothesis. So yeah, I guess here I should ask, who remembers what are conditional probabilities? 1 person, 2, 3, 4, 5, 6. Okay, then I should stop and explain conditional probabilities. So conditional probability in Bayesian statistics is literally the most crucial definition, and that's something you would have to understand to use it somehow. It's defined by probability of x, and this vertical line means condition and given y. So, for example, you want to know probability of a person being hungry considering 2 events. So probability of hunger given, and there can be maybe, in our case, 2 hypotheses. Either the person had a dinner, this is deep, or the person had no dinner. So this is 2 binary hypotheses. The person either had a dinner or not. So we may say that total probability of a hunger equal probability of having a dinner multiplied by probability having hunger given dinner plus probability of not having a dinner multiplied by having hunger given no dinner. So, well, stupid question, but which is higher, probability of having hunger with dinner or without dinner? Someone? Yep. So that's an intuitive thing, that it's still probability of being hungry, but conditioning on different observation about a person, they might change drastically. So we usually may estimate probability of having dinner, probability of having no dinner, which is, equal 1 minus probability of having dinner. And yeah, that's what conditional probabilities are. It's just something about a person or about a subject you want to study, and that affects your interpretation, your confidence about some other facts about the subject. And that again links back to the definition that probability is a measure of our uncertainty. So ideally, if we can condition on all the facts in the world, we would expect that this probability would either be strictly 1 or strictly 0. So usually, if your probabilities are close to 0.5 or something weird, then you just don't have enough conditions, and you want to understand what data can you add to your model to make these probabilities closer to some definite values. Is it clear? All right. So now we are back to this definition. So probability to observe data given null hypothesis is basically our p-value, or not exactly, whatever. So we can write these two probabilities and measure their likelihood, and basically say whether it's more likely to observe null hypothesis or alternative hypothesis, and how much more likely is it. So it does not give us a good threshold, because thresholds usually suck. Like y 0.05, I can tell you the story how it emerged, and it's really weird. So this threshold of 0.05 is mostly random. And reporting exact values, particularly here, likelihood ratio, is much more fair way to deal with our data. There are also other criteria, like a Akaike information criterion, Bayesian information criterion, which people use. They are a bit weird, but usable in many situations. And if you want to learn more, I really suggest this book. It's easy to read and explains the stuff. Yeah. Sure. Just in case, I will send the link to these slides to Slack, so you will be able to see it. And most of my presentations are open, so should stay open forever.
That's I think that's a good moment to talk about the information content criteria, because when we are doing Akaike criterion or Bayesian-based criterion, there's a kind of discrepancy between them, because they are put emphasis on different parts of the model.
Sir, can you repeat the last part about a bit louder?
Yeah, I asked about when should we use, in your opinion, of course, Akaike criterion and when Bayesian criterion, because they may be, when you are comparing several models, they may not agree with the scoring of different models. So do you have any opinion or perspective which one is more applicable?
Yeah, that's a really long discussion. I mean, proper answer to a question would require a whole 1 hour lecture about how they work. So very simply, and I don't want to disappoint you in Bayesian statistics, only in this particular criteria, is that people, when tried to infer them, they wrote a whole likelihood about our model and tried to make a fair assumption about, all the probabilities. Then it turned out that we don't know 90% of the assumptions there, and they replaced them with normal distribution, and that's totally not true in many cases. So some assumptions of Akaike criterion are a bit more suitable. Some assumptions of Bayesian criterion are a bit more suitable in other cases. None of them is universal. None of them is perfect. They are both very far from perfect. So that's particularly why I don't even want to explain them here, because in practice, I don't use either of them because they are both just so theoretical.
Okay, so it depends.
Yeah, and maybe you should pick something different altogether.
What do you use in practice?
Well, when I build my models, I usually estimate full likelihoods and just this kind of likelihood ratio or similar.
But it doesn't take into account number of parameters.
It does not, but your common sense does.
Okay, right.
And it's usually more reliable than those criteria. Any other questions? Let me also check the time. So, okay. Then another way to validate your Bayesian model is basically when you do, for example, regression, you can always estimate confidence intervals, and you can plot them. So, for example, like you are fitting your curve to a data, and then you may say that with, for example, 90% chance your data would lie within these boundaries, and with 99% chance your data would lie within these boundaries. And plotting these boundaries is really extremely helpful. So you might see them for those who work with R. Let me just show it here. Like there is this kind of smoothed curve, geom smooth. Which shows you intervals like here. So that's exactly like you may set up like confidence intervals for the curve. They're usually like pretty strict, so it's not like 99%. But yeah, plotting these confidence intervals wherever you do regression is really helpful, because in some cases, like here, you just would totally see that your model is incorrect. Well, you can see it without them, but a bit easier. In other cases, like here maybe, you can start comparing your models and see that, like, for example, there is overlap, and here you probably cannot decide precisely which model is applicable on this interval. And yeah, in some other cases you can. So yeah, plotting confidence intervals show you your uncertainty, show you like magnitude of difference very often. So please do that if you do some Bayesian analysis. Then, of course, when you fit your model, you may, well, what you care about is what's the, like, how likely that you make another experiment and the model would still generalize to that experiment, so that the model is reliable for different data sets or like for different samples. And here Bayesian statistics use kind of the same framework as machine learning does, or vice versa, machine learning uses the same framework as statistics. You may take your data set, you split it in two parts, like training and testing. It's kind of imitation of this whole exploration confirmation stages, but you do it on the same data set. It just, you take training set, you fit a model there, and then you try to predict the testing set and see how well it predicts that. So if it's regression, it's like just how far they deviate from your predicted values. If it's classification, then what's the proportion of samples which are classified correctly. And yeah, that way you can just, having a small set of data sets, test how well your model performs and get some ideas about its ability to generalize. Yep, that's kind of it on the first theoretical part. So, some comparison of Bayesian with p-values. I don't think we should spend much time on that. So, do you have any questions about all I just said? Or about statistics, or like in general?
So basically, how do you use Bayesian statistics in practice?
Oh, that I will show you on the next part. We will take actual papers and we'll go over them and we'll try to build models and see how they perform.
You might be discussing this later as well, but does it help you kind of say with some level of confidence, if I have this many number of replicates for a study, I would have this much confidence in saying that there is an effect or no effect?
Do you mean estimating confidence level from the number of samples?
Yeah, kind of. Like,
Yeah.
or how many replicates would I need so that I can say with this much confidence that there is no effect?
Yeah, that's a very good question. And that gets to this example. So splitting data on training and testing set. So for example, that's how we applied this kind of stuff on, well, that was very trivial model, but still, like in our paper, we tested how differential expression models like perform on different samples. So the question is like, if you have like 10 control samples, 10 disease samples, and you run differential expression, how stable is that? Or if you have 5 versus 5, so exactly dependency of like confidence on your results from the number of samples. And then basically what you do is you have 5 versus, like imagine you have 20 samples, like 20 versus 20. Then you exclude 1 and run all the results. Then you exclude 5 and run DE multiple times, excluding different 5 samples, and estimate like your expected expected differentially expressed genes. And basically, for each number of samples, when you reduce the number of samples, you would get some score of like. Well, too bad. So, you have number of samples, and you have your confidence, which is like, in our case, was number of differentially expressed genes, which, so like you had a set like S20, which is a set of genes on all the samples, and then you take, for example, like here 15, and the question is how many samples of these 15, how many genes when we run DE on these 15 samples are the same as when we run DE on 20 samples. So basically we try to test prediction quality of our gene DE on subsamples. And then by excluding different 5 samples, you would get something like this. So like some variation. You can do the same with maybe 10, and it probably would get lower. You can do the same with 5, it get even lower, and then you get like 3, and it's like close to 0, for example. And that may be, I don't know, 0.8. So what you do, regression, 1, and then you estimate that maybe you need here, like, I don't know, 30 samples. Yep.
What about permutation of bootstrap when we're missing samples to check if we get more samples, if we actually get better results?
Well, I mean, in this case, like permutation, like how would you suggest to use that?
So if I explain correct, you split the samples and randomly assign them, and then you try to predict.
Not randomly, no. So we have like a set of like maybe control, and it's like 10 samples, and disease, and it's like 10 samples. So the split is always there. We don't call diseased samples control in any case. We want to test for real differences. What we do is we randomly exclude samples from control and disease. Maybe like randomly 5 from here, or like 3 from here, 2 from here. So we just randomly exclude samples. And that gives us fewer number of samples, and that gives us here basically our uncertainty. So this is our confidence intervals.
But in your paper, have you obtained this linear dependency?
It was not exactly linear, no, and
I read in some paper that it goes like this, so the more you do You don't have, like, it doesn't influence it.
That is correct. Like, in most cases, when you do these kind of things, you have a saturation curve. So first it starts going up fast, and then it kind of saturates. But you still can feed this curve and predict how many samples you need, like at the end.
Or if you have 10 samples, you have like 300 and something from that.
No, you cannot.
Still to be able to say how many you would need to actually get something meaningful.
Not really. I mean, 3 is like most extreme case because there is no way to downsample at all, like not even once. Of course, you can. What can you even do in that case? Nothing, I guess. Just do more samples. Or check the previous study and realize that you need at least 10. Yeah.
Yeah, I think it's because a lot of like studies on like mice, for example, they use 3 replicates for a condition. So it's kind of difficult to.
That's a huge problem. I mean, I can show you results from the paper, and really 3 versus 3 is almost never enough. So, I mean, you can get some significant p-values, but, you know, we do genes by p-values, and yeah, what is your guess? If you have 10 versus 10, and then you exclude just one sample and do DE, so the difference of having 9 versus 10 and 10 versus 10, how many genes would you expect to preserve in this case? Most of them is like how much percentage? Just I mean, by 80%. Any other guesses? In our results, it was close to 40%. So, you know, you get significant p-values. The test is mathematically correct, but the confidence in your results is like 40%. So if you get 3 versus 3, it's something ridiculous there.
But the majority single-cell sequencing studies have one conditional, like one knockout, one wild type. That's a majority, like vast majority of
These
studies.
are old studies. I believe journals stopped accepting them these days.
No.
No?
No. In the wet lab field, where people mostly like care about do single-cell sequencing and not about like how you do statistics, one and one is normal.
Okay, well, I'm glad I didn't work with such studies. Yeah, but I mean, in this case, like with 3 versus 3, you can at least just, I mean, it's hard to argue that it's not enough because, you know, 3 is a number, but in case of 1 versus 1, or 2 versus 2, it's easy to show that it's mathematically impossible to get anyhow reliable results. So, yeah, I mean, even in theory, it is impossible.
But there is some paper, it was published recently, that they created algorithm how to create artificial replicates. Like when you want to do this seq2, you have like 2 samples, let's say, 2 replicates, but you do like bootstrap, which you said, and it's artificial replicate, and it like helps to improve the analysis. So like, well, it's possible to have small amount of samples if you have a lot of practice in such stuff.
I didn't read that paper, so I do not know how they did it, but like just the theory behind the problem is that it's really hard to model inter-individual variation. Just you are so different from me by so many parameters that even if you take 2 samples, then like maybe, you know, we are kind of the same age, maybe we are both male, and then we take the 3rd sample, and the difference is then immediately huge by any random number of factors which we cannot control for and which we don't know how to model in terms of variability. Because for a random disease, like take something new which no one ever studied, and then we don't know whether there are like sex differences, whether it is age related, whether like it's affected by smoking, by lifestyle, and so you need to have a very representative sample of all these conditions to even start modeling the difference. So unless you control for all these conditions and you know how they affect it, like all kinds of subsampling would not guarantee you anything. I can imagine that they improve results somehow, but I wouldn't trust in that.
But if you have 10 samples and you bootstrap, then it's more likely that you get like more robust results later because you have more variability in 10 samples than you do in 3, for example, or...
If they are representative, like, I mean, again, it's very often that you get, for example, all your disease samples are like, I don't know, child cancer or whatever, and or like not child, but like yes. So for example, like from 15 to 20, but then you get your healthy samples, and it turns out that you actually took dead people like in age, so they like of average age of 70. And I mean, I saw a lot of such studies. So you might take 50 versus 50 and still not trust the results. But generally, yes, you're correct. Like 10 versus 10 is better than 3 versus 3.